Tired of walking down the stairs? An engineering student of mass m designs an ingenious device for reaching the ground from her dorm room. A block of mass M at rest on the ground is attached to a rope that passes over a pulley. The student grabs the other end of the rope and steps out of her window a distance D above the ground. Determine the velocity of the student when she reaches the ground as a function of m, capital D, and little g. So again, we have the mass of the student is m, the mass of the block is capital M, but this time, if the student is going to go downwards, capital M should be less than little m. We are also given the distance instead of the time. When we do the free body diagram for the student, we have a force mg acting downwards, that's the force of gravity. For the block, we have a force mg acting downwards, that's also the force of gravity. And we have the tension in the rope acting upwards, but because we called it F rope in the last problem, let's call it FR again here, but you could call it capital T for tension. We use the definitions to fill out the table. The definitions are kinetic energy is equal to 1/2 mv squared, gravitational potential energy is equal to mgh, work is equal to sum of the magnitude of the forces other than gravity times the magnitude of the displacement times the cosine of the angle between the force and the displacement. Okay, so for kinetic energy, well, let's say this is the student and this is the block. Event 1 is when the block is at rest on the ground, so we don't say block is released. We would say the student steps out of window. And I guess event 2 would be when the ground is reached, since the student is going downwards. Okay, so the student is at rest to begin with, well, steps out of the window, but not giving themselves any initial velocity. So KE1 is 0, the block was at rest on the ground, so KE1 is 0 for the block as well. The student starts at a distance capital D above the ground. So we're going to say the ground is equal to 0. So the student has an initial gravitational potential energy of mg capital D. The block starts on the ground, so the block starts with the gravitational potential energy of 0. If the student goes down a distance capital D, the block goes up a distance capital D. So this would be capital M times G times capital D. We are looking for the velocity of the student when she reaches the ground. So we have 1/2 mv squared for the kinetic energy when the student reaches the ground, but we're looking for little v, so little v is an unknown. And the kinetic energy of the block, 1/2 mv squared. Because work energy is a scalar function, I did not have to pick a positive direction in order to fill out the table. You do have to worry about how the direction of the force compares to the direction of the displacement here, but you still don't need a positive direction to do that. You only need to know how these directions compare. Gravitational potential energy is 0 for the student when she reaches the ground. This is work done by forces other than gravity, so that's just the force of the rope acting upwards. The student is moving downwards. So the displacement is pointing downwards. That's the direction that the student is moving in. This is the same as the direction of the velocity. So we have the force of the rope acting upwards. The displacement is downwards. So over the cosine of the angle between the force and the displacement, we have a negative sign. So this is minus FR. That distance, the displacement, is capital D. Then for the block is moving upwards since the student is moving downwards. So the displacement is upwards, same direction as the force of the rope. So for the cosine of the angle between the force of the rope and the displacement for the block, we have 1. So this is FR times D. Also, you could just say, instead of doing the cosine of the angle between the two, you could say work is positive when the force is in the same direction as the displacement, or the direction that the object is moving in, and it's negative when the force is in the opposite direction of the displacement, so you could do that also. And remember that this is the work done by forces other than gravity, because We already included gravitational potential energy, so don't include the force of gravity when you do the work if you are looking at gravitational potential energy, as the change in gravitational potential energy is equal to negative work done by force of gravity. I can do the bar graph now. So kinetic energy for the student is 0 initially, kinetic energy for the block is 0 initially, gravitational potential energy for the block is 0 initially, and the mass of the student is greater than the mass of the block. So if I say the initial gravitational potential energy for the student is 2 blocks on my bar graph, the final gravitational potential energy for the block should be less than that because the mass of the block is less than the mass of the student. So the distance is the same, but the mass is smaller, so we should have smaller gravitational potential energy. And remember that KE1 plus GE1 plus work 1, 2, other, is equal to KE2 plus GE2. GE2 for the block is equal to 0. And work is negative, kinetic energy is positive, so let's do a small amount of kinetic energy here, so like half a block there. And this plus this is equal to this, so if this is 2 blocks and this is half a block, my work must be negative 1/2 blocks. So this plus this is equal to this. Look at the work that you have for the student and the block. They have the same magnitude but the opposite sign. So this would be a block and a half if the work done for the student was negative 1.5 blocks. Kinetic energy is positive. Oh dear. So that can't be the gravitational potential energy that I have if I have this work for the student, because I need to have some kinetic energy. So that's going to take away from what I have here. So if we just make this 1 block instead, that would work. I could also change the work here, but then I have to change the work there also. Okay, so that would be a good bar graph because it shows the correct relationships, but I'm not going to worry that much about the bar graphs when I'm grading your homework as long as the signs are correct, and you should show that this equation is true for the bar graphs. Okay, but if you don't show that this work is equal to that work, well, that's okay. So now I can take my work energy relationship, KE1 plus GE1 plus work 1, 2 is equal to KE2 plus GE2, and I can use this for the student and for the block. If I use the definitions to fill out the table, at this point I can just take everything I have in the table and put it into this relationship and I should be good. This is for the student. KE1 for the student is 0, GE1 for the student is mg capital D. The work is minus FR times capital D. KE2 is 1/2 little mv squared. GE2 is equal to 0. Now I do the same thing for the block. 0 plus 0 plus FRD is equal to 1/2 capital M V squared plus capital MGD. Now, if this is equation 1 and this is equation 2, I'm going to use my personal favorite method for solving 2 equations and 2 unknowns, which I can do in this case because if I just add the 2 equations together, this minus FRD cancels with this plus FRD, so just add them together and the force of the rope cancels out. And that's good because we're looking for the velocity. We have 2 unknowns in this equation, just like we did in the previous problem. We don't know the force of the rope. We don't know the velocity. We're looking for the velocity, but since we don't care about the force of the rope, I can just add these together and the force of the rope goes away. So to add the 2 equations together, add everything on the left-hand side of both equations, add everything on the right-hand side of both equations, and I get 1/2 m little v squared plus 1/2 capital M little v squared plus capital MGD. And I can bring the capital MGD over to the other side. Capital M GD. Then I can pull out the 1/2 v squared, capital M plus little m. Now I can divide both sides by 1/2 little m plus capital M, or multiply both sides by 2 and then divide by little m plus capital M. I could pull out the GD on the other side of the equation. So this is little m plus capital M. Remember that the mass of the student is supposed to be greater than the mass of the block in order for this to work. So this should be positive. I pulled out the little g times d, and I'm going to multiply by 2, so that's 2GD. I'd be left with this equal to v squared, so I can take the square root, and I get v there. Now, if you tried to do this with a block that had a larger mass than the mass of the student, you'd be taking the square root of something negative, and you would get an imaginary velocity, because the situation you wouldn't have the student actually going down in that situation. If little g is equal to 0, what should v be equal to? So this is like what we did last time. If you're doing this in the far reaches of deep space where there is no force of gravity, the student steps out of the window and doesn't go anywhere because there's no force of gravity to pull the student downward. So we would get 0. And if little g is equal to 0, I get 0, and yes, that agrees. If the masses are equal to each other, I would expect to get 0, but remember that you could actually make it work in that case if you jumped a little bit or pushed yourself off of the window sill downward. So does it agree? If the masses are equal to 0, I get 0 there. Yes, it agrees. So assuming the student just steps out of the window, if the masses are equal, the student would not go down. If little m is equal to infinity, now it's the student who's going downward. If the student's mass is equal to infinity, it's like the block isn't even there. And if the block isn't even there, the acceleration would be equal to little g. We said last time that v would be equal to g times capital T in this case, but that doesn't work so well here because we don't have the time. We have the distance instead. So if I do a little bit of kinematics, then I would get a velocity of the square root of 2 times g times capital D. So I should get v is equal to the square root of 2gd by kinematics. And that does agree with what I have here. If the mass is equal to infinity, I have to use the same trick that I used last time. So I can multiply in the numerator and denominator by 1 over little m, and that gives me the velocity is equal to 1 minus capital M over little m, 1 plus capital M over little m times 2gd, and this is equal to 0 as m goes to infinity. This is equal to 0 as little m goes to infinity, so yes, it agrees. I'm not going to show all the work for this, but it's doing kinematics, and if you want to go through it on your own, you can do that. So that concludes problem 152, and that concludes Model 1.